Hi, this is Felix from NMR, and today I want to introduce you to our favorite hyperpolarization method, which is photochemically induced dynamic nuclear polarization, or also called photo-CIDNP or photo-kidnap. And the goal of this video is to provide you the basics without entering necessarily into heavy mathematic formalism, so that after this video you can deep dive into reviews and the original paper and you already have everything you need to understand this process. So why do we want to do photo-kidnap? The goal is to increase the sensitivity of NMR, which is pretty limited otherwise. As you know, photosensitivity is the difference between alpha spins and beta spins, and this is proportional to the energy gap that you have between these two spin population, and the thermal, and inversely proportional to the thermal energy that you bring to your system. So to increase sensitivity, there are some obvious approaches from this equation. One is to increase the concentration, so you increase absolute number of spins that you have and the delta n. You can also reduce the temperature, so that you reduce the thermal energy that you bring to your system, and then you will have more alpha than beta spins, or you can increase the magnetic field. But in our case, we do life science applications, so we always need to be pretty limited in terms of, pretty low in terms of concentration that we have between micromolar and millimolar, and we also need to operate in temperatures that are relatively high, so often above 273 kelvins. And same for the magnetic field. This can be increased, but I think the most, at this time of the video, the highest magnetic field commercially available is 1.2 gigahertz or 28 teslas. And this means that this is also quite a big investment. So not every lab has the chance to buy such an expensive magnet. And this does not really increase your sensitivity. This is much more for resolution. So we use other tricks. We use hyperpolarization methods, as I mentioned, and we are then able to artificially manipulate the spin states, keeping the same delta E and keeping the same thermal energy. And we then are able to obtain a much, much higher signal to noise. And by doing so, we are then able to measure low concentrations much, much faster than what we'll be able to. And there are diverse hyperpolarization methods, and the topic of today is to focus on one, as I said, photo-kidnap. So what is photo-kidnap in a glance? In a glance, photo-kidnap is a pretty simple process. You put your molecule of interest right in your sample, like M, which can be tryptophan, and you put a photosensitizer to your sample. Very classically, we can put fluorescein or riboflavin. And you will shine light in your sample. You will illuminate your sample, and this will trigger the photo-kidnap process. And at the end of this process, you will have hyperpolarized molecule M, as well as the photosensitizer that will be hyperpolarized. And these molecules, now they are hyperpolarized. They are the same molecules, but with higher, with a different, much bigger difference in the nuclear spin state, like beta and alpha. And they just relax back to their ground state with the longitudinal relaxation. So as you can see here, for the black spectrum is without illumination. So this is before we trigger this photo-kidnap process. And after this photo-kidnap process, we were able to achieve a much higher signal-to-noise enhancement. I think here we have about 70-fold signal-to-noise enhancement in this case. So we are going to walk through the photo-kidnap process step by step, and we are going to explain why we start from a molecule M to end up with an hyperpolarized molecule M. And there are different steps that we are going to explore. The first one will be to explore photosensitizer excitation. Then we are going to look how do we form a radical pair. Then we are going to have a quick look at the radical pair mechanism, which is what will create the hyperpolarization. And then the radical pair can recombine back to their ground state, so they're not radicals anymore. They become back to ground state molecule, but they are hyperpolarized. Some of the radicals do not recombine directly. They become escape product, and they also contribute to building hyperpolarization. So we go back to our first step, which is the photosensitizer excitation with light. And you already probably know this scheme where you have your photosensitizer, which is in the ground state, and we shine light at the photosensitizer. It gets excited and it forms an excited singlet state with an electron that jumps to an orbital of a higher energy level. And most of the time, what happens very, very quickly is that you have fluorescence that happens, so that this electron goes back to its ground state by emitting back a photon. But in some cases, it's a much less frequent process, but it can still happen. You have an intersystem crossing, or here written ISC, and this intersystem crossing will be essentially an electron spin state transition or flip. It will flip to the other spin state. And here you see that you have now a triplet state. Okay, so a triplet state is when both of the electron spins have the same orientation. And what happens is that this electron cannot go back to its lower energy orbital level. And this is then a forbidden transition. This is why we have phosphorescence, for instance. So our goal is to generate this triplet photosensitizer state because it's long-lived and it can then have the time to diffuse and meet with other molecules. And this is what will trigger then the radical pair formation. So you can see it's why we have these nicely colored samples when we do photo-kidnap. And here this is a mock-up benchtop of the photo-kidnap setup that we have in the NMR. So you see that we can shine light to our sample and obtain a very, very bright sample. It's quite beautiful. Once we excited our photosensitizer with light, and this is now in the triplet state, our radical pair or photosensitizer will be able to form a radical pair. So you see the triplet state molecule now is close to the molecule M, and an electron transfer can take place from the molecule M to the triplet state photosensitizer. And once this electron transfer took place, we now have a radical pair with the photosensitizer that has an additional unpaired electron and the molecule M that has an unpaired electron lacking one electron. And in principle, due to the energy levels, we will suppose that this electron could transfer very quickly back to the molecule M. But because of the spin conservation, we formed this radical pair to be a triplet state. So you see this radical pair is a triplet state here, and the Pauli principle forbids that this electron can be transferred to the molecule M. So we will need to have this system to become a singlet state by having one electron that flips, but this is forbidden as well because there is something that is called the electron exchange coupling that forbids the triplet singlet state mixing. And this electron exchange is distance dependent, so as long as those molecules are close to each other, they cannot have this triplet to singlet mixing. So we have this cage radical pair that is actually relatively short-lived, although we have two different charges. So we have one that is minus charge, which is a photosensitizer, and one that is plus charge, that is the molecule. But this has a lifetime of about 10 nanoseconds or something in this range. So now we formed our radical pair. We formed it as a cage, okay? And we have this cage radical pair where nothing happens. We are stuck, essentially. So now we are going to enter into the radical pair mechanism. And to understand the radical pair mechanism, let's look at it first in a very high-level overview, where we have first our radical pair that you have here, right? That is a cage radical pair. But I told you it's very short-lived, and after a few nanoseconds, it will diffuse apart. So we have now the two molecules that are relatively far away, and the electron exchange coupling will disappear. After that, after a few microseconds, we have an increased probability that these two molecules meet each other again. This is diffusion theory. I will come to that later. And there is this increased probability to encounter again and form again a cage radical pair. And as I told you, initially it was in the triplet state, and now the singlet to triplet mixing state could happen. Okay? And when they meet again after a few microseconds, they will be either in a singlet state or in a triplet state. When we look at it now with a view on the electronic structure, we have exactly the same thing here. We start from a triplet state radical pair, they diffuse apart, and now they can have this triplet singlet mixing, and they will meet again to form radical pairs that can be either in triplet state or in singlet state. So you see that one electron here, one electron spin state flipped. But what is driving this triplet singlet mixing? So what drives the triplet singlet mixing is the fact that these electrons are resonating with the magnetic field. So the spin orbit coupling of the electron spins, it's the G factor, and in interactions with the magnetic field, we have then a resonance at a given frequency. So each molecule has a different G factor, and then has a different resonance in the magnetic field. This is true for the photosensitizer here, as well for the molecule that you can see here. So what happens when we look at the rotating frame, we have initially a triplet state, and then these electrons, they start to process in the magnetic field, and we will have a dephasing with time. Okay, so we have a dephasing with time because they don't have the same frequency. So after a while, we will have, for instance, a singlet state because the dephasing reached the moment when we have a singlet state. And this is a frequency, as you can see, right? It turns and goes back between singlet and triplet state. And this has a frequency as well. So this dephasing frequency is actually the frequency of triplet singlet mixing. And this is the difference in between the two resonances of the photosensitizer and the molecule. So you see the formula of singlet triplet mixing is then the delta G, the difference between the two G factors, times the Boltzmann constant times the magnetic field. This tells you why we have triplet singlet mixing, but it does not tell you yet why we have hyperpolarization. And to understand why we have hyperpolarization, we need to dive a bit deeper and add a new coupling constant, which is hyperfine coupling, which is the interaction, the coupling of the electron spin with the nuclear spins. So depending on the nuclear spins, we will have now a slightly different resonance. And when we introduce now the hyperfine coupling for the molecule M, we see here that we have now a beta spin, and we will have then the resonance due to the G factor minus the hyperfine coupling times the spin state, which is minus 1.5. And now you see that we have a smaller frequency, a smaller resonance frequency for this electron. And this means that we also have a smaller difference in this frequency and a smaller frequency of dephasing. So it dephases less fast, meaning that the triplet singlet mixing frequency for the beta spin state is smaller. And you see here it's basically the same frequency as earlier, minus 1.5. And when we take now an alpha spin, okay, we now introduce the hyperfine coupling constant, okay, for this alpha spin, and we have now plus 1.5. And in this case, we have now a higher frequency of resonance for this electron. Okay, and now we have also a higher frequency of dephasing. So it dephases faster than for the beta spin. And it also appears in the formula of the frequency of triplet singlet mixing. For an alpha spin, you have now the initial frequency for the G due to the G factor difference plus the contribution of the hyperfine coupling. So here you have minus 1.5 and here plus 1.5. The other interesting thing is that the G factor difference contribution is magnetic field dependent, because when you reduce the magnetic field, you will reduce this overall. But for the hyperfine coupling, this is not magnetic field dependent. This is always the same independently of the magnetic field. So you see that you can play around the field and around the G factor to modulate the photo-kidnap that you want to have. And now, what did we say? We say that these two spins, these two molecules, they form initially a radical pair, they diffuse apart. We have now this triplet singlet mixing, but at some point they will re-encounter. And they will then split, re-encounter, and after a time tau, which is a probability that is calculated from diffusion theory, after this time tau, we will have these spins to re-encounter and form again radical pairs. And what we now know is that for the beta spin, the beta nuclear spin, we will have more triplet states, okay, than singlet state, because the triplet singlet mixing time is slower than is slower, so we have more triplet state that is formed than singlet state. But for the alpha spin, we have more singlet state because the triplet singlet frequency is faster, so we have more singlet state that is formed at the end of this process than triplet state. And this is the end of the radical pair mechanism. So you see, we formed more triplet states, we formed more singlet states radical pairs at the end of this mechanism for the alpha spin than for the beta spin. And now let's see how this builds up during the radical pair recombination to yield to hyperpolarization. It's pretty simple. We just need to join these things together because those are all the same molecules. So if we just look at it this way, we see now that the singlet state molecules, they have an hyperpolarization. Okay, you see that they are hyperpolarized. They have more alpha spin states than beta spin states. Although they have less spin state overall, they have more polarization. And this is quite interesting. So you have now hyperpolarization for the singlet spin state. And what can happen in this singlet spin state is that now we can do the electron transfer. And when we have this electron transfer, these are not anymore radical molecules. They are ground state molecules, and they are observable with NMR because they are diamagnetic, and they are hyperpolarized. For the triplet state molecule, what happens is that we have the opposite polarization because we have now more beta spins, beta nuclear spins that yielded to triplet state radical pair than alpha nuclear spins. So we have here the opposite polarization. Here we have +2 and here we have -2. But these triplet state molecules, they cannot recombine because this electron transfer is still forbidden by Pauli principle. So at the end of this process, we call this the Germinate polarization. This is the first cycle of photo-kidnap that we completed. And you see that the singlet yielded to ground state molecule and the ground state molecules, and the molecule M is polarized with a polarization equal to, and it will decay with R1, so the longitudinal relaxation, which is in the seconds time scale. The triplet state radical pair that were formed by the radical pair mechanism, they remain radical molecules and is polarized with the opposite sign, P equal -2. So it formed again cage radical pairs that can break again, and now the radicals will escape in the bulk. Okay, the transient radicals, so those are transient radicals, right? So why do we not get P equals 0, right? We know that they are transient. At some point they will go back to the ground state and they have P equal -2. And this happens much faster than in the seconds. So why it does not just cancel out? To understand that, we need to look at the escape product. And now we can look at the escape product. So we go back to what we had before. So we had ground state molecules now. Okay, we have ground state molecules that have hyperpolarization equal to, and we have triplet state radical pairs that have an hyperpolarization of -2. So let's just keep in mind that we have this polarization of 2 for the ground state, and let's now remember that these cage radical pairs, they can now escape, they can split and separate and go in the bulk. Okay, they just diffuse apart from each other, and they still have this hyperpolarization of -2. But what happens is that those molecules are radicals. They have they are paramagnetic, and then they are subject to paramagnetic relaxation, which takes place in a few microseconds. And therefore, we have now a polarization of 0 because the nuclear spin states now relax back to the thermal equilibrium in a few microseconds. So now we see what we have here. If we count the points, we see that we have now the ground state molecules, okay, that we mentioned before, the one that could recombine. They have a polarization of 2, but the free pairs, the radical pairs that escape from each other, they diffuse in the bulk, and they went through paramagnetic relaxation, those ones, they have a polarization of 0. So we know now that the overall polarization is 2. Okay, we have now hyperpolarization. But this is not completely over. And these 3 pairs, they are as well able to contribute to the hyperpolarization. So these 3 pairs, now they are in the bulk and they are able to meet randomly with other radicals. So when a radical photosensitizer meets with a radical molecule, they will meet and their spin state can be of 4 different kinds. Okay, so when they meet, they will randomly form either singlet state, and then do singlet state, they can then recombine and become ground state molecules, but their polarization is 0, so they do not contribute to the hyperpolarization of the system. Okay, so this is just lost hyperpolarization, and they can meet in a triplet state. I did not mention that to you earlier to not confuse you, but now I must say that the triplet state can be of 3 different kinds. We have T plus, T minus, and T0, and only T0 is able to do radical pair mechanism. When they meet in T plus and T minus states, they will just meet and then split apart again and go to the bulk again and go through this random process. But the T0 state, which is the one that we saw earlier, it can go through radical pair mechanism, and this will yield to a polarization equal to posed by the number of spins that that go through this step, but it yields to the same hyperpolarization through radical pair mechanism as we just saw earlier. So you just need to go back in the video and look again what happened in this radical pair mechanism. So now we count the points again, and what we see is that we have the Germinate hyperpolarization, and after that we now do again 1/4 of this Germinate polarization, so 2 divided by 4, because only 1/4 of the radical pair that are formed from 3 pairs are able to yield to hyperpolarization, so but to the same extent, so 2 divided by 4, and in the third cycle we will have again 1/8. Okay, so 2.2 divided by 4 times 1/4, and this is 1 divided by 8, so 1/8. So you see that we keep adding up again and again a little bit of hyperpolarization, and those cycles take a few microseconds. So usually we say that in around 100 microseconds all those cycles are completed. So now we can formalize a little bit more. I promise that we don't do too much heavy mathematics, but this should be okay, I guess. So you see that the polarization, what is it? It's the Germinate polarization, PG, okay? And this is now plus 1/4 of PG, okay? Here it's not PG, this is the free radical pair polarization overall, and because those next cycles of radical pair mechanism that will add up polarization, and one cycle of hyperpolarization, which is a radical pair mechanism, the amount of hyperpolarization will depend on the number of radical pair that you formed earlier with the triplet state photosensitizer and the molecule M, and times the hyperfine coupling divided by the difference in G factor and the magnetic field. So you see, if you want to improve, or if you want to increase the hyperpolarization that you generate, what you can do is to either select molecules that have a very high hyperfine coupling, or select the dye, the photosensitizer and the molecule to have close G factor. So like this, you have a small delta G, or you can also reduce the B0 magnetic field. So of course, what you want to first improve is the yield of your radical pair formation. Okay, so for that you can play on the generation of triplet state photosensitizer, and as well on the electron transfers that will yield to a higher number of radical pair formation, and on the efficiency of your radical pair mechanism. And there's a rule of thumb that A should be around half of the delta G, the product of delta G, the Boltzmann constant, and the magnetic field. This is in the high field theory. When you go to, I must say that when you go to low magnetic field, so below 1 Tesla, you start to have much different mechanism. So everything I mentioned is for the high field theory, which is what interests us today. So, step by step, how can you play around the efficiency of your photo-kidnap process? You can, as I said, play on the photosensitizer, okay, at this step. So you can select a photosensitizer that has a high quantum yield and a long triplet lifetime. And that will enable you to have optimal condition, because as well the concentration will play a role, as the triplet state photosensitizer can quench itself by energy transfer. So you see that you need to keep a relatively low concentration of your triplet state. So you need to then have a longer triplet lifetime, but you also need to have a high quantum yield. So you can play on the properties of your photosensitizer to be optimal for photo-kidnap. And those properties of the photosensitizer will also have an influence in the radical pair formation, because you need to match the redox potential between the photosensitizer and the small molecule, so that the electron transfer is efficient. And then you can optimize your radical pair mechanism. So I always write sin square times the frequency of the spin triplet, the triplet singlet mixing time times tau. And here, sorry for the beta, you can just ignore this, but here this is the probability of being in a triplet state, in a singlet state. So the probability of being in a singlet state is sin square of this product. So you can optimize this so that you obtain more. And you see that the tau component is the time for at which the radical they recombine. So you see that this is a diffusion controlled reaction, and you can play around that by, for instance, modifying your solvent, the viscosity, or the temperature to change diffusion and diffusion properties of your system. You can also play on the hyperfine couplings that we mentioned, so you can select molecules that have high hyperfine couplings, but in general, this is not something you usually want to hyperpolarize a molecule regardless of its hyperfine coupling. So I would say that you play more around the delta G, so we optimize which photosensitizer we select, and as well the B0, the magnetic field. So as I said, you can also increase the tau, for instance, to have diffusion control, and then you have more dephasing. But it's a frequency, so at some point it may come back. So that's it for this video. I hope that this was useful to understand the very basics of photo-kidnap. And if you feel that you already understood quite a lot with this video, I would highly recommend that you read those reviews. And I put them in these orders for a reason. It's not because I want them to be backward in time. It's because they go from the most high level and easy to read into more accurate mathematic formalism, and all of them are very, very good. So I would really recommend to read each of these reviews in this order, and this is accessible to undergrad students from master level with a bit knowledge of biophysics and even limited knowledge in quantum mechanics. This is relatively easy to read, but I will also suggest that you have a look at it from an historical perspective. And I selected a few articles. There are many more, but a few very, very important articles are, of course, the ones that were kidnap, which was not photo-kidnap. Kidnap was discovered in 1967, and you will see that these two discovery was done independently in the same year, which was quite funny that it happens independently. And what happens as well independently is that when 2 years later, two different groups solved the radical pair mechanism in 1969, and there are different letters in 3 parts. In the description of the video will be the link to all the articles. Later came the role of diffusion in the radical pair mechanism, and this was introduced by Adrian in 1970, and this was based very, very heavily on the noise theory of diffusion published already in 1954. So you see, this is pretty much old science, but we still use it very, very much nowadays. And looking at it is very interesting as well to understand how people discover something new and how do they so quickly understand what is happening in there, because you see here there is a span of 3 years. This is quite amazing to read at it, and there's also a lot of work from Fisher that you can look at to have a good understanding of photo-kidnap. So I wish you a very good lecture, and I will stop here. See you next time.